PCO2 by a respiratory quotient of 0.8, then that number that I get will tell me how much oxygen is consumed to produce the CO2 that's on the numerator. Okay, we know the CO2 in the numerator is 40 millimeters of mercury. If I divide that by my respiratory quotient, 40 divided by 0.8 gives me 50 millimeters of mercury of oxygen. Okay. So I have to consume more oxygen, okay, than CO2 is generated, if that makes sense. In breaking down all of those nutrients that we use to produce ATP, more oxygen is consumed than CO2 is produced. And the ratio there is 0.8 that you use in the denominator to figure that out. Okay? So that in producing 40 millimeters of mercury of CO2, partial pressure of CO2, I consume 50 millimeters of oxygen. So that's being removed from the alveoli. So we drop our partial pressure of oxygen drops from 150 in the airway, and within the alveolus it falls to 100 because of the fact that oxygen is constantly being consumed. In fact, there's a little equation to calculate the partial pressure of alveolar oxygen. This large case A represents the alveolus. So the partial pressure of oxygen in the alveolus can be calculated this way. Okay. I can figure out the partial pressure of oxygen in the airways by taking atmospheric pressure minus 47. 0.21, we've done that. And then subtract the CO2 in the alveolus divided by 0.8 times respiratory quotient. This is really a figure that generates the amount of oxygen that's being consumed. So if I subtract the amount of oxygen being consumed from the oxygen content within the airways, then I get its partial pressure within the alveolus. Did everyone follow that? This is an area where some of you will start to get lost. I understand that. Yes? The 150 is the partial pressure of oxygen here within the airways. Okay? We say that because oxygen is being consumed in the alveolus, it's going to drop. Its partial pressure in the alveolus is going to drop. Okay? Depending upon how much is being consumed. Now, these are the partial pressures of oxygen and CO2 coming into the pulmonary capillaries from systemic veins. This is blood that's already given up its oxygen and picked up CO2. So, as this blood then enters into the pulmonary capillaries, we see a gradient of partial pressure for oxygen. 100 millimeters here in the alveolus, 40 millimeters here within the capillary blood. So when oxygen crosses this membrane, it's going to cross from the alveolus into the pulmonary capillary blood following its pressure gradient. By the same token, CO2, because its content here in the blood is higher than it is in the alveolus, it's going to move from blood to air following its pressure gradient. That makes sense, everyone? And by the way, because these gases move so quickly, equilibrium is going to be achieved by the time that blood is leaving, okay, and entering into the pulmonary veins. So the blood that enters into the pulmonary veins generally has a PO2 of 100 and a PCO2 of 40, the same that we see here. In fact, if you were to measure these values within systemic arteries, like the radial artery, they would be very close to these measurements here. because this blood is moving directly back to the left side of the heart, and it's being pumped to all of the systemic arteries. So when we do blood gases, we measure these values, PO2, PCO2, within the arterial blood. And those values can be very close to the measurements if you could obtain them from the pulmonary venous blood. We're just moving this blood from point A to point B. JJ, you with me? Okay, how many people here at this point are lost? It's a safe environment. Okay, anybody else? What do you, so tell me, what are you struggling with?
Why, that's a dumb question. Why is that like so low?
Why is what so low?
Mixing
Why is
compared to like everything.
this here?
No,
On the other side.
This here, I'm sorry. Well, because here, this blood that's traveling to tissues gives up its oxygen. And so it's going to lose oxygen such that its partial pressure is going to fall from 100 to 40. Okay? And then at the same time, this blood carrying a partial pressure of CO2 of 40 is going to pick up more CO2. And so that when it returns, it's going to have a higher CO2 content, a higher partial pressure. Does that make sense? So what happens after this is internal respiration. Oxygen's going to leave, CO2 is going to be picked up, and then it's going to return to the lungs. JJ?
Okay, how you said, how does, this is going to be really long. How do you say blood flows from the pressure, the area from higher to lower?
Right, it goes from an area of higher partial pressure, okay? And the partial pressure simply reflects its dissolved concentration.
Right.
Okay, so if it's got a higher concentration in one area than it does in another, it's going to flow from that area of higher concentration into an area of lower concentration.
Okay, and that's what it did.
And I'm using these units of partial pressure to describe that concentration. And that's what's happening here. Oxygen is going to move from an area of higher concentration, a partial pressure of 100, into an area of lower partial pressure when it's only 40. Okay.
So that's going to go down there.
Yeah, in other words, oxygen is going to move from alveolus into the pulmonary capillary blood.
Right.
And you can think of the alveolus as kind of looking like this. Okay. The total volume of the alveolus compared to the pulmonary capillary is significant. Okay. So oxygen is going to move rapidly enough that by the time the blood reaches the pulmonary veins, that equilibrium has already been achieved. So that now, PO2 of 100, PO2 of 100. Are you with me?
I'm going to get there.
So the equation that was in the middle,
Yeah.
that just describes that whole
Right.
process?
Right, it says the alveolar PO2 is 150, okay?
Right.
That's taken at 760 minus 47 times 0.21. And we're simply subtracting the PCO2 divided by the respiratory quotient,
Which we found.
which we
The-
know about
the 50.
through experiments.
Oh, that wasn't what we found. The
Well,
50
yeah,
millimeters of mercury over
yeah,
there.
if it's 40 divided by 0.8, that's 50.
Okay.
So 150 minus 50 is 100. Okay. So what's the determinants of PO2? It's determined largely by adequate pulmonary blood flow and oxygen consumption. Okay? This PO2 here is largely determined by how much oxygen is being consumed. As it's consumed, it's removed from the alveolus. And we showed you how you could figure that out. It's based upon the amount of CO2 that's being produced. And then we could say the same thing about the determinants of PCO2. You have to have adequate pulmonary blood flow, and it's determined by how much CO2 is being produced. Okay? This CO2 here in the alveolus is a reflection of how much the tissues are producing. Now, at normal ventilatory rates, here, if we have a minute ventilation of 4 liters per minute, okay, which is normal, which is average, then the alveolar PO2 is around 100. The alveolar PCO2 is around 40 at normal ventilatory rates. What would happen if you hyperventilate? If you hyperventilate, you're going to blow off CO2 at a rate greater than it's being produced. And so the alveolar CO2, as you increase ventilation, is going to fall. So with hyperventilation, you become hypocapnic. I used that word the other day, hypocapnic. You're blowing off CO2 at a rate faster than it's being produced. And of course, if you're hyperventilating and bringing in oxygen into the alveolus at a rate faster than it's being consumed, then the alveolar PO2 is going to climb higher than it would otherwise. So now, if you hypoventilate, if your minute ventilation decreases, and we move from right to left on the x-axis, and look what happens to the alveolar PCO2. It climbs. Okay? Because we're not blowing it off as quickly as we should. So CO2 within the alveolus is going to be beginning to climb. We're not expelling it at the same rate at which it's being produced. So its concentration, expulsion pressure begins to increase. Okay, let's talk now about oxygen transport within the blood. Oxygen is transported in the blood in 2 forms. And we mentioned this the other day, that a small amount of oxygen that's transported within the blood is in the dissolved form. Okay, it's dissolved really in plasma. That makes up about 1.5% of the oxygen in the blood. The other 98.5% is combined with hemoglobin to form oxyhemoglobin. Okay. Now, if we talk about oxygen content of the blood, okay, the way we traditionally discuss oxygen content is by using units of volume. Okay? Oxygen content is the volume of oxygen carried in 100 millimeters of blood. And it's going to equal the sum of both the dissolved oxygen and that which is chemically combined with hemoglobin. So to discuss the total oxygen content, you have to add these 2 forms of oxygen together. Now, there's a theoretical maximum oxygen carrying capacity of hemoglobin. Theoretically, each gram of hemoglobin can carry up to 1.39 milliliters of oxygen. Okay. That's a theoretical maximum. In practice, direct measurements give a maximal capacity that's closer to 1.34 milliliters of oxygen per gram of hemoglobin. So this is the number we're going to use when we try to calculate how much oxygen is bound to hemoglobin. 1.34 milliliters of oxygen per gram of hemoglobin. In other words, in ideal states, each gram of hemoglobin can bind and carry 1.34 milliliters of oxygen. Okay? So total oxygen content is the combination, the sum of both the dissolved oxygen and the oxygen that's bound to hemoglobin. Let's go back in time and let's think back to our hemoglobin molecule. It consists of 4 globin chains, each of which houses a heme unit. In the center of that heme unit is an iron atom to which oxygen can bind. Oxygen, when it binds to the iron atom within the heme group. So, when oxygen binds to hemoglobin, okay, we now refer to that hemoglobin as being oxyhemoglobin. Hemoglobin bound to oxygen. If we know the hemoglobin content of the blood, then we can calculate the oxygen carrying capacity of that blood, the amount of oxygen that can be carried by hemoglobin. How do we know the hemoglobin content? We perform a CBC. A CBC will tell us the hemoglobin concentration and the hematocrit. Well, we're going to use the hemoglobin concentration. It's expressed in grams per deciliter, or grams per 100 milliliters of blood. 100 milliliters is the same thing as a deciliter. Okay? So, I'm going to take that value that I obtained from the CBC, and I can multiply it times 1.34 milliliters of oxygen per gram. And that product is going to give me the maximum oxygen carrying capacity of hemoglobin of that person's blood. Now, of course, if someone's hemorrhaging and their hemoglobin content falls, well, so too will their oxygen carrying capacity. Because most of the oxygen is carried by hemoglobin. So if you lose hemoglobin, if you lose blood, then your maximum oxygen carrying capacity is going to be reduced. That's why people who are severely anemic are short of breath. They don't have the same oxygen carrying capacity. Now, what we just discussed was the maximum oxygen carrying capacity of hemoglobin. In most cases, hemoglobin is not 100% saturated. Okay? In other words, it's only 100% saturated if every hemoglobin molecule within the body is carrying 4 molecules of oxygen. And oftentimes, the percent saturation is less than 100. Okay? How do we figure out the percent saturation? It's the amount of oxygen that's actually bound divided by the oxygen carrying capacity. That number we figured out right here. That goes in the denominator. Oxygen carrying